All right, let's do some examples involving Stokes Theorem. So here we're asked to use Stokes Theorem to evaluate a surface integral of curl. And the whole point of using Stokes Theorem is that it gives you an alternative to computing this curl integral. So if I was just to compute this integral directly, I'd want to compute the curl of f, parameterize the surface, and then evaluate the surface integral. But Stokes' theorem says, why not instead compute the line integral of f dr, where C is the boundary of the surface S. So that's what we're going to do. First, let me get an idea about what this surface is. Apparently, it's a paraboloid pointing downwards above the plane z equals 1, so it looks something like this. And so its boundary is the bottom circle, like that. And the surface is given to be oriented upwards. So actually the direction that I drew on the circle on the bottom is positively oriented. So if you are sort of walking around that curve in this counterclockwise direction, facing in the direction of the normal vector, then the surface is to your left. If I had oriented it the other way, then it wouldn't be positively oriented relative to the orientation of the surface, with the normal going up. Okay, so in order to compute this line integral, of course, I want a parameterization of that curve. So the curve is at level z equals 1, I guess. And let me see the circle that x and y make. Well, it's the intersection of the plane z equals 1 with this paraboloid. So if you evaluate this, you're getting a circle of radius 2 in x and y. And we know how to have x and y traverse that circle. We do 2 cosine t and 2 sine t. And so if I just let t run from 0 to 2 pi, then this will be a parameterization of that curve. Okay, so what I'm saying is that this is the parameterization of the curve. In order to evaluate the line integral f dr, I'm going to need the r prime. Excellent. And I think I'm ready to compute the integral then. So I'm going to evaluate the vector field, which is this, at the parameterization. I take the z component squared, which is 0, minus 3 times x times, oh, not 0, sorry. Looking at the wrong one. So the z component squared is 1, and then negative 3 times the x times the y. And then x cubed, y cubed. Okay, there's f evaluated at the parameterization, and then I dot this with r prime. All right, and here's my integral in t to evaluate. Let's do a substitution here. Letting u equal cosine, du will be negative sine, so that works out nice. Okay, and cosine is the same at 2 pi as it is a 0, so this thing evaluates to 0. All right, so there's an example of computing a surface integral of curl using Stokes' theorem. You could imagine that the direct computation would be sort of a mess. I mean, computing the curl of the vector field S might be complicated given all the complexity of the component functions, I guess, and then parameterizing this surface and all that. So sometimes this saves you a lot of time. This wasn't such a bad line integral to compute. All right, let's use Stokes' theorem in the other direction. So this example asks us to compute this line integral of this vector field, and instead of parameterizing C, we're going to compute a surface integral of the curl of this vector field across the surface that's bound by this triangle. Sometimes they'll ask you to compute the work done by this vector field in moving a particle along this curve. That's just another way of asking about a line integral, because we know that work done is the line integral of the field. Yeah. Okay, so let's get a drawing of what this curve is and see the surface it bounds. So I've got 1, 0, 0, 0, 1, 0, 0, 0, 1, and the curve is a triangle oriented counterclockwise when viewed from above, so that would look like this. Okay, there are many surfaces that this triangle bounds, but most immediately a plane surface, right? So I could try and take a surface integral over this triangular S. That would be the most reasonable thing to do. So instead of computing this line integral, I'm going to use Stokes' theorem, which tells me that it is equal to a surface integral of the curl of the vector field F dot ds. So let's crank out curl. So some of these partial derivatives are 0. For example, the partial of x with respect to y is 0. Okay, there's the curl of f. Now let's try and parameterize this surface. So we can see here that the plane that is this surface is, well, if you do a couple different things, you can figure out the formula for this thing. One thing you could do is create two vectors contained in the plane and take a cross product to get a normal. You could start with the general form of a plane, ax plus by plus cz equals d, and then just plug in these 3 points. In any case, you'll end up with this as the equation of that plane. And I see that since z is a function of x and y, there's an easy parameterization I could do of this surface that just lets x and y be the parameters. And I'll just check really quickly that that usual parameterization is oriented in a way that C is positively oriented with that orientation. I did not say that well, but that's what I'm looking for. And if not, I'll just switch the role of the parameters. Okay, what I'm saying is an easy way to parameterize that surface is to let x be a parameter and y be a parameter. You don't actually need to introduce 2 new variables, but I like to do that. So this is a parameterization of that plane, and I could think about, the xy plane is the same as the uv plane. And so this surface lives above this triangle in the xy plane. So I want to bound the parameters appropriately. So u or x goes between 0 and 1, and then v goes between 0 and 1 minus u, like that. So that describes this parameter space for that surface. And then I check really quickly, like if I'm, on the plane right here, and I look at r sub u, it'll go in this direction, and r sub v will go in this direction. So ru cross rv is a normal going out this way. So here's the curl of a vector field, and I'm going to plug in the parameterization. All right, I'm just getting RU and RV, and then the cross product, of course. Oops, that's 1, 1, 1. Yeah. And then I'm ready to roll. Okay, so there you have it. That is a computation of the line integral of this vector field around the triangular curve by using Stokes' theorem to instead compute a surface integral of the curl of the vector field across this triangular surface.